Welcome to another explainer from Optatube. Today, we're pulling back the curtain on the real workhorses of the power grid. Those massive power plants that give us the steady, reliable electricity we pretty much take for granted every single day.
You know, every time you flip on a light, you're plugging into one of the most complex machines on Earth. And a huge reason it's so reliable comes down to a specific type of power plant that has to follow a really strict and honestly fascinating set of rules. So let's break down what those rules are.
Here's how we're going to tackle it. We'll start with what these plants are, then get into why they're so controllable. After that, we'll break down the nitty-gritty rules they have to live by, and finally, we'll see how it all fits together into a giant daily puzzle that keeps our grid from going dark.
All right, first things first. Let's get on the same page about exactly what kind of power plants we're talking about today.
We're talking about thermal units. So think of your conventional power plants, the ones that burn fuel like natural gas or coal to create heat, which makes steam, which spins a turbine to generate electricity. For a long time, these have been the absolute backbone of power grids all over the world.
And right away, we run into this core trade-off. On one hand, these things are incredibly reliable. They just work. But that rock-solid dependability comes with a price tag, both in the cost of fuel and in their impact on the environment. For grid operators, it's a constant balancing act.
Now, this brings us to their single most important feature. It's the one thing that makes them so critical for managing a modern power grid.
The key word is dispatchable. This is everything. Unlike solar or wind, where you're kind of at the mercy of the weather, grid operators have direct control. They can literally pick up the phone and dispatch an order to turn a unit on, shut it off, or dial its power output up or down. That control is what makes the whole system work.
But having that control isn't as easy as just flicking a switch. These are massive, complicated machines, and they are governed by a really complex set of rules, both technical and economic.
And this quote really gets to the heart of it. You can't just run these plants any way you want. Every single decision has to be optimized, finding the absolute best, most efficient schedule that also respects all of their physical limitations.
This whole process, this giant puzzle, has a name. It's called unit commitment. It's the daily challenge of deciding which units to commit or turn on to meet the country's electricity demand at the lowest possible cost, all without breaking any of those tricky rules. If you get this wrong, you're looking at blackouts or just wasting millions of dollars.
So, what are these rules? What are these constraints that make unit commitment so challenging and so interesting? Let's break down the most important ones.
First, you've got the basics. When a thermal unit is on, it can't just run at zero. It has a minimum level it has to stay at to be stable. We call that P-min. And of course, it has a maximum output it can't possibly exceed. That's its P-max. So it has to live somewhere in that range.
Next up is cost, and this is where things get really cool. It is not a flat price per megawatt hour. The cost to run one of these units actually follows a curve, a quadratic function to be exact. Let's look at what each piece of that formula, the A, B, and C, actually means for the grid.
Okay, so that A term, that's the no-load cost. Think of it as the price just to have the unit on and synchronized to the grid, even if it's just chugging along at its minimum level. The B term is what you'd expect, the basic linear cost for the fuel you're burning. But that C term, that's the kicker. It makes the cost curve bend upwards, which means each additional megawatt you want to generate costs a little bit more than the one before it.
And you can see that effect right here. As the power plant's output goes up, the cost to produce that next block of power is higher than the last one. Why? Because generators get less efficient as they get pushed closer to their limits. The big takeaway here is that more power isn't just more cost, it's proportionally more cost. And this is super important because it's often what sets the market price for electricity for everybody.
All right, let's talk about time. You can't just toggle these giant plants on and off. Because of all the heat and mechanical stress, once you fire up a unit, it has to stay on for a minimum number of hours. And on the flip side, once you shut it down, it needs a minimum amount of time to cool off before you can safely start it up again.
On top of that, they can't change their output in the blink of an eye. Every unit has a maximum speed at which it can increase or decrease its power. We call that its ramp rate. It's like the acceleration limit on a giant cargo ship. It just takes time to speed up or slow down.
So, let's look at a quick example. If a unit is sitting at its minimum of 50 megawatts and its ramp limit is 50 megawatts per hour, it's going to take a full hour to get up to 100 megawatts, then another hour to get to 150, and so on.
You can see how operators have to plan all of this out hours in advance.
So let's put all of these different pieces together and just take a look at the huge puzzle that grid operators are solving, not once in a while, but every single day.
See, it's not about just one of these constraints. It's about all of them, for hundreds of different power plants, all at the same time. You've got to respect the min and max power, calculate those tricky nonlinear costs, factor in how much it costs just to start them up, obey the up and down times, stay within the speed limits, and even hold some power back just in case. It's a staggering optimization problem. And obviously, they're not doing this with a pencil and paper. They rely on incredibly sophisticated unit commitment models. That's powerful software that takes in all this data and spits out the most cost-effective and reliable schedule to keep the lights on for all of us.
As you can see, this is a seriously complex optimization problem. If you are interested in energy markets and power system modeling, and you want updates and insights about the global energy market, then you should definitely follow the Optatube channel. So after all that, what are the most important things to remember?
Well, first, thermal units give us that flexible power we desperately need, but it's a constrained flexibility. It has rules. Second, every decision isn't just about now, it's about on-off states, complex costs, and rules that connect today tomorrow. And finally, these constraints aren't just a nuisance, they are the absolute heart and soul of the models that keep our grid stable.
And all this leaves us with a huge question for the future. As we add more and more variable renewables like wind and solar to the grid, this kind of rule-bound, predictable flexibility that thermal units provide, it becomes even more valuable. The real challenge is going to be figure out exactly how to value it and how to optimize it in the energy system of tomorrow. Thanks for watching.